Let's take a look at some probability. This is a way of looking at the likelihood of events. We could determine if things look rare or not rare. So in an in-class experiment, suppose that we attempted to catch a quarter from our elbows using both our left and right hand. Let's suppose we were successful with the left hand 15 times out of 25 trials. Let's suppose with the right hand we were successful 20 out of 25 trials. We might wonder, how can we visualize the data? Is there a relationship between the hand that we used and the success rate? And what is that relationship? So to try to come up with a visual, I'm just thinking I might try something like a table. So maybe I have left hand and right hand. And maybe I have catch and miss. We get even more information in this table. I might want to know the total number of times that I caught, the total number of times that I missed, total number of attempts with the left, total number of attempts with the right. So I'm going to add an extra row. Rows are like when you row a boat, rows go side to side. An extra row with the total. I'm going to add an extra column. Columns are like buildings where they go up and down, columns of buildings. I put a total here as well. I'm doing these double lines just because it kind of look like equal signs to me. I'm adding things up. With the left hand, we caught 15 times. This is 15 catches with the left. In total, we did 25 attempts with the left. So that means that we miss 10 of those times. 15 and 10 gives me 25. Looking at the right hand, this is also out of a total of 25 attempts. Caught it 20 times. So 20 and 5 gives me 25. By having these totals on the outside, I can make sure that things add up vertically and horizontally. If I did 25 with the left and 25 with the right, I did a total of 50 attempts. Adding the total number of catches, 15 and 20 gives me 35 catches. 10 and 5 gives me 15 misses. This still doesn't help me answer this last question here of looking at the relationship between my catch rate and the hand that we used, though. And I want to understand this table a little bit better before we try to answer question C here. I even want to give this table a name because this gives me a lot of really nice combinations that I didn't have with my original data. So for example, I can see that there was a total of 35 catches. That wasn't immediate from here. I'd have to add these together. The misses would have taken a bit more work. The misses with each hand was something I was lacking altogether. So the name of this device is a contingency table. Let's go over the construction for these, and then let's make a couple and try them out. So in some situations, we don't have centers and standard deviations to figure out if something is rare or not rare. We can't use the definition of unusual. Instead, we look at the likelihood of events using probabilities and tables. And we just made a table, but here's how we would do them in the future. We're going to put one category in the columns. So for example, catch and not catch, or maybe catch and miss. We're going to put the other category, left hand and right hand, for example, in the rows. On the outside of the table, I'm putting my totals, and then I'm going to fill in all of the remaining grid as I go along. I'm also going to give you a little bit of early exposure to some language stuff. We created a contingency table on the last page. But we're going to see these words and or show up while we're talking about these tables. So I want to get a little bit of early exposure to it. First off, in stats, when you say the word and means both things have happened. So for example, if I say, I want a candy that is red and sour, it has to be both red and sour at the same time. The word or in stats refers to either thing happening, possibly both together. So and is restrictive. It gives you less options. You want those things together. Or is inclusive. It gives you more options. So someone might ask you, what's the probability that you caught it or you used your right hand? They might also ask you, what's the probability that you catch and use the right hand? So let's get that table back up here. Catch and miss or not catch. Another column here for the total. I like to use 2 lines. If you use a straight edge, your line's going to look a lot better than mine. And we had 15, 20, 35, 10, 5, 15. Grand total of 50. These are the numbers that we started out with. If I'm saying or, then or is going to be anywhere with catch as an option. And let's highlight those squares up. These are all the spots with catch, and we're just using these inside numbers when we add stuff up. If we use the total, we would be using the 15 and the 25 to get the 35. If we added the 35 again, we're kind of double counting. So we're just using the inside numbers. And we're going to combine this with anywhere with the right hand option, which in this case would be anywhere here. All of these things are considered successes. Catching with the left, that's catching it. That's at least one of those 2 things. Catching and right, great, you happen to have both. Missing but using the right, you're still using the right hand. That's considered a success here. So if I'm looking at this probability, I'm going to add these numbers up. I've got 15 and 20 gives me 35. 35 and 5 gives me a total of 40. Probabilities are always ratios out of the overall totals. In this case, this is out of a total of 50 individuals. Typing this into a calculator, 40 out of 50 gives me a decimal of 80% here for the or. Let's check out the and language. And when you see the word and, you should really think both. This is where those things meet up. So this would only be the spot with both catching and right hand meeting. So it would just be that single value here of 20. So this probability, the intersection, is 20 out of the total of 50, and that's 40%. Reviewing these elements before we look at another example here. I have one variable as the columns. I have another variable as the rows. When I see the word or, this is giving me more options. Or gives you more. When you see the word and, that's working like the word both. It's where those things meet. It is restrictive. So let's try another one. We're bringing all these elements in. So suppose I have 60 plants in my garden, and 40 of these things I grew from seed, and the rest of them I bought from Al's garden. Already with just this information, I can start to build a table because I have some things I got from seed, and some things I have from Al's garden. That's one of the variables. I'm going to keep reading, and I see that 15 of these plants are vegetables and the rest are not vegetables. So I have veggies and not veggies. Ten of the vegetables were from owls. So these combination of events, vegetables and owls, those things happen on the inside of the table. There are 60 plants in total. That's the overall total. So I'm going to put that in the lower right corner here, 60 total. 40 things were from seed, and the remainder of 20, 40 and 20 gives me 60, were from owls. 15 of the plants in total were vegetables, and the rest were not. So 15 and 45 add up to 60. 10 of the vegetables were from owls. So 10 are owls and veg. So the and is where they're meeting. I'm going to find the rest of these values just by adding and subtracting things. 5 and 10 would give me 15, so this should be a 5. 5 and 35 would give me a 40 here. 35 and 10 would give me 45. And to verify vertically, 10 and 10 gives me 20. A couple questions that you might want to know about this. Let's kind of break it up for the different subgroups. We're learning how to look for relationships. Out of all plants. So this is out of the 60 plants. What proportion were vegetables? Well, 15 out of the 60 were vegetable. So the probability of veggie is 15 out of 60. We type that into a calculator. And when we do so, we get that there was a 25% chance that a randomly selected plant from my garden happens to be a vegetable. Out of plants from owls. So this is saying don't use the whole table here. Restrict it to only those from owls. So I'm going to cover everything else up here, except for those owl plants. Here I'm seeing that the total is 20 possible plants that I'm looking at. And from this group of 20, it's looking for something that's a vegetable. Well, out of this 20, 10 are veggies. So this gives me a 50% chance. So for the plants from owls, 50% of them are vegetables. Out of all plants, 25% are vegetables. So it looks like there's a higher proportion of vegetables that I'm buying from owls. Let's look at the non-owls plant, the seeds. If it's out of this group, out of seed, that's going to have the total for seed here, 40. Inside of that group of 40, I'm going to look back up. I'm looking for vegetable. 5 of the 40 are veg. I'm going to type this into a calculator and see what I get. and I get 12.5%. So let's kind of write down what's going on here. So out of all plants, 25% are vegetables. Out of the plants from owls, 50% are vegetables. And out of the plants that I grew from seed, not from owls, 12.5% are vegetables. So in this problem here, it looks like there's a relationship between where I'm getting the plant and if that thing is a vegetable or not. In particular, it looks like the highest percentages of vegetables are coming from owls. I'm most likely to be buying these types of things from owls. And if I'm growing them from seed, they're more likely to be non-vegetables. Looking for a relationship has a name, and that's checking for independence. We say two events are independent if the outcome of one does not affect the outcome of another. Now that might be a little bit hard to understand, so let me rephrase this another way. Two events are independent if there is no relationship. The probability does not change if you're looking at different subgroups. In this problem here, though, the probability did change. So in the situation where you would see a change in probability, we say the events are dependent. Dependent means there's a relationship. In this case, that relationship would be more likely to have something be a vegetable if you know it's from owls. Using this language, I want to revisit that table from the start here, and I want to know, are the events of catch rate and hands used independent, and why we might care about that. So what I really want to check here is, what does the probability of catching look like for each of the hands? So let's consider the probability of catching if you used the left hand. And let's compare this to the probability of catching if, or out of, you used your right hand. For this data set, if you used your left hand, then you're looking at that top part of that table there. This is out of those 25 trials. And there were 15 successes out of the 25. Typing this into a calculator, I get that there was a 60% catch rate for the left. If the events are independent, this ratio would have to stay the same. That would mean there's a 60% catch rate for the left, and there would have to be a 60% catch rate for the right. If the numbers stay the same, we say the events are independent. If the numbers change, we say they're dependent. Let's look at the right. For the right hand, out of the 25 trials, we were successful 20 out of the 25 times. Typing this into a calculator, 20 out of 25, I get a success rate of 0.8 or 80%. Writing down what this means, there is an 80% catch rate for the right. these ratios are different. So the events are dependent. The likelihood that you catch or miss will depend on which hand you use. In particular, we are more likely to catch the coin if we used the right hand. So this is why we might care about this, because this is really telling me the relationship between these variables. Statistics is all about trying to figure out how things are related. This is one of those connections. As we're going through these problems, another one of my goals is just to improve our notation and make this language a little bit easier to understand. So that way we don't have to write down as many words like if and out of and given. So a little bit of notation that's going to help us out is this vertical line, which means out of. So if I want to know the probability of A, if I assume B to be true, I write it A given B. So for example, if I'm writing catch vertical line right, this is really asking what's the probability of catching if or out of you use the right hand. And we found this on that first page, catching if we use the right hand, to be this 20 out of 25 number. So catch given right was 20 out of 25, was 80%. Reading this one, probability of catch given or out of left. Probability of catching if you use the left hand. And for that group, we saw that we had a success rate of 15 out of 25, or 60%. Here's some other vocab pieces related to this, just name-wise, so we can get used to it. If you see the phrase out of, this is telling you that you're going to be looking at that specific subgroup. If you see given, if there is a known quantity, if you're dealing with an if style problem, these are all indications that you're going to be limiting the subgroup. When you are finding these probabilities, you're going to have on the bottom the thing that it is out of. So if it's out of the left hand, or if you use the left hand, you're going to have the total for the left showing up on the bottom. This looks like you are dividing by that amount, so divide by that amount. I want to label two earlier problems using this kind of notation. Out of plants from owls, what proportion are vegetable? This was dividing by plants from owls. So I would have the vertical line and then owls to say divide by that number. The amount that I wanted on the top was the proportion of vegetable inside of that owl's food. For this next ratio, I was dividing by the amount of seed out of seed. I'm dividing for given seed. I'm looking for the proportion of vegetable inside of that. So I'd have veg come first. You may notice that in these problems, the probability of veg given owls and veg given seed, these were different ratios, and that gave us a dependent relationship. Likewise, when we compared our left-hand catch rate, 60%, with our right-hand catch rate, we noticed that we were better with the right hand instead of the left hand. If events are independent, you will see that the catch rate for the right hand should be the same as the catch rate for the left hand. Events are dependent if the probability of catching with the right hand is different than the probability of catching with the left hand. Using these phrases again, if they are equal, this is telling you everything looks the same. This means there's no relationship between the variable. It doesn't matter if you use the left hand or the right hand, your catch rate remains the same. In the situation where those ratios are changing, we would say the events are dependent. And in this case, we would say there is a relationship between those variables. More generally, two events are independent if the probability of A given B or out of B is the same as the probability of A given that B has not happened. In other words, if you're using the left or the right, if you're using seed or owls, if you're looking at any two different subgroups and the probability of success stays the same for each of them, then the events are independent. I'm going to pause this for a second, and I would encourage you to pause this for a second as well. Stretch your legs and then come back to check out what's going on with using a different device, namely a tree. Okay, we looked at combinations of events. This next page is going to look at sequences of events. So ignoring the hand use, what are all possible catch and miss combinations we could have in the next 3 attempts? So let's just use C for catch and the letter M for miss. One combination I could have is I could have a catch on the next 3 attempts. I could catch the first 2 and miss on the third. I could catch the first and the third, but miss the second. I could miss the first and catch the next 2. I could have 2 misses and then a catch. A miss, catch, and a miss. A catch and then 2 misses. Or I could have 3 misses in a row. The set of all possible outcomes, these sequences here, is called the sample space. So this is everything that could happen. Now, if I wanted to try to visualize this, I could make some sort of a tree diagram, something that would show what could happen for each possible throw. So let me try to draw this out just to see what this looks like. So this first set of branches here is either a catch or a miss. This represents the first throw. Let's see what can happen on the next one. I could have a catch and then a miss. So this would represent a catch and then a catch. This would represent catching on the first and missing on the second. So these are doing a lot of work for me to keep track of these sequences to make sure I don't miss them. The third one could be a catch or a miss again. Which gives me a tree that looks something like this. Now I'm going to write out the combinations at the end, seeing what these sequences look like. Catch, catch, catch. Catch, catch, and then miss. Catch, miss, and a catch. Catch, miss, and miss. A miss, a catch, and a catch. A miss, a catch, and a miss. Miss, miss, catch. Miss, miss, miss. I have all 8 combinations for things that could happen here. And by making this tree, it is easier for me to keep track of all of those things that could happen. Let's look at another situation. Let's consider a drawer with 20 batteries. And I'm going to check these batteries one at a time until I get either a good battery or draw 3 batteries, whichever comes first. And let's look at the sample size here. So sample space. So my first pull could be either a good battery or a bad battery. I'm going to keep pulling until I get a good one. So if I got this good one here, this would be an ending spot. So one possible ending sequence here would be just getting that good battery and then stopping. If I got this bad one, I would keep pulling them. And the options for those next pulls, this could be either good or could be bad. If I got this second pull of a good, a bad, and then a good, I would stop here because I have that working battery, I'm good to go. So the combination B and then G would also be a stopping sequence. If I had 2 bads in a row, I would keep pulling. And this third pull could be either good or bad. If it's good, I would stop there. I got that working battery, even if it took 3 tries to get it, bad, bad, and good. I would stop at this bad battery as well, though, because after 3, I just get tired and stop. So if I have bad, 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 that would also be an ending spot for this tree. This would give me a sample space of good, bad and good, bad, bad and good, and bad, bad, bad. So some of these trees are nice and symmetric. Depending on the context, it might just be a partial tree. Not only do these keep track of these changing events, we'll see that they also keep track of probabilities. So more generally, when I'm making a tree, branches appear in bunches and they represent events. So for example, this first set was either catch or miss. And I could have 3 or 4 things in a set of branches, like maybe these are flavors of candy. And I have cherry or mint or strawberry, so I could have 3 or more branches. Subsequent branches assume that the first thing has happened. So this good here assumes it's a bad and then a good. To find these probabilities at the end, we're going to multiply the probabilities along the way. This takes a little while to get used to, so let's practice a couple together. Let's use that data from the first page where I had a catch rate, overall catch rate of 35 out of 50, or catch rate of about 70%. Create a tree for what can happen in the next 3 attempts at catching a coin. Using this tree, calculate the probability of making all 3 catches, making 2 of the 3 catches, 1 of the 3 catches, and none of the catches. So this first set of branches, I either catch it or I miss it. There is a 70% chance that I catch it, which means that my probability of missing is 30%. My second try is either catch or a miss. And I'm writing the probabilities on the branches as I go to help me keep track of what can happen. So this catch, writing that probability, 70%, miss, 30%. I'm 2 in, let me go 3 in, catch, and miss, catch, miss, catch, miss, and a third one, catch, and miss. The probability of catching is 70%. The probability of missing is 30. As you can see, this tree is already getting kind of big. So my hope is that if I were to do a larger one, something with like 5 sets of branches, eventually I'd come up with a better technique for doing this. So let's count how many times we catch it going through these sequences. So at the top, I have catch, catch, and catch. So the number of times that we catch here is 3. Catch, catch, and miss. The number of times that I catch here is 2. Catch, miss, and catch. The number of times that got caught there is 2. Catch, miss, and miss. The number of catches here is 1. Miss, catch, and catch, that's 2. Miss, catch, and miss. The number of catches here is 1. Miss, miss, and catch. That's 1 catch. Miss, miss, and miss. That's 0 catches. And to find each of these ending probabilities, you are going to multiply the branches as you go. So let's look at some of these probabilities together. So let's suppose I want this probability of catch, catch, catch. To find this probability, I'm going to start at the beginning and I'm going to multiply the probabilities on the way. So I have 70%, 70%, and 70%. I'm going to type this into a calculator to see what I get. And when I do so, I get a 34.3% chance. Let's look at catch, catch, and miss. Catch, catch, miss. I'm going to multiply the probabilities on the branches on the way. So I have 70 for the catch, 70 for the catch, 30% for the miss. Doing this gives me 14.7%. Next one, catch, miss, catch. 70 for the catch, 30 for the miss, 70 for the catch. When I type this into my calculator, I get 14.7% again. And you might see this when you're working with a tree. You might see some of these probabilities repeat. That's okay. Catch, miss, miss. Catch, 70%. Miss, 30. Miss, 30. I'm multiplying the probabilities as you go. You can even see what these are when you start to list them out. Catch is 70. Miss is 30. Miss is 30. You are multiplying sequences. When I do this, I get a probability of 0.063. Miss, catch, catch. Miss is 30, catch is 70, catch is 70. When you're writing these probabilities, you can write 0.30 or 0.3. That means the same thing. When I do this, I get 147 again. I'm going to keep going. Miss, catch, miss. The probability that I miss is 30%. Catching is 70%. Missing is 30%. Typing this into a calculator, I get 0.063. Probability, just keep going down the line here. I got two more. Miss, miss, and catch. 30% for the misses, 70% for the catch. Gives me 0.063 again. And finally, probability of 3 misses in a row. The probability of each of those misses is 30%. I'm multiplying those numbers together. Doing so gives me 0.027. The tree helps make sure I don't lose any of these sequences. When I'm using the tree, when I'm using the sequences, you are multiplying the numbers along the way. If you see multiple spots in the tree that work, when you're trying to find the probability of 3, 2, 1, or 0, you're going to add up all those results. So the probability that you get 3 catches only showed up here at 34.3%. If you wanted the probability of 2 catches, you'd have to add up all these probabilities for 2 catches. In this case, that looks like that 14.7 showing up 3 times, giving me a probability of 44.1. So if someone said, how likely is it that you got 3 in a row? There's about a 34% chance at that. The probability that you got 2 out of 3 was 44%. The probability of getting 1, I'm going to add up all the probabilities for 1. Looks like I had the same thing showing up 3 times here. Gave me 18.9%. And the probability of 0 only showed up 1 time at the bottom of the tree. Probability that I miss all 3 is pretty low at about 2.7%. I want to use this tree again for another situation. This tree is going to be slightly different than the last one, though, because I'm doing this for a drawer with 20 batteries, and I'm supposing 16 of those 20 are good. And I'm going to draw batteries until I get 1 good one, or I draw 3 batteries, whichever comes first. So the first set of poles here is it's either good or it's dead. Unlike the last one where I could keep catching and missing all day long and it would stay 70% for catching and 30% for missing, this time I'm removing batteries as I go, so I might see these probabilities change. So for example, on the first pole, I have all 20 batteries, 16 of which are good, 4 of which are dead. If I get this good battery, I stop. But if I get this dead battery, I keep going. I got to be careful here because something has happened. Namely, before I can move on to this next set, I have to acknowledge that the total number of batteries has gone down by 1. I've removed a battery from the drawer. In particular, the battery that I've removed here is a dead battery. So this means I'm now looking at these totals as being out of 19 because I've taken one of them away. I've not touched the good batteries on the sequence down here, so I still have all 16 good batteries, but I've decreased the number of dead batteries, which used to be 4, by 1 to get a new value here of 3. So this tree will keep track of these changing probabilities. If I get this good one, I stop. If I get this dead, I keep going. I'm going to keep pulling until I get either 3 or 1 good battery. If I keep going after this pull here, I will have taken out 2 dead batteries in a row. So the total will have gone down by 2. And that's because I have removed 2 of the dead batteries. If 4 were good at the start and I've taken away 2, I only have 2 more remaining. If I started out with 20, I have 18 left. If I've done nothing but pull dead on the bottom, I've not touched those 16 good batteries. 16 out of 18 would be good here. 2 out of 18 would be bad. If I get 3 good, I stop. If I get 3 period, I would also stop drawing. So this is what the tree looks like when it's done. Let's use it to answer a question. Draw a tree, done. Find the probability that at least one battery was good. Well, I have all the spots in my tree here boxed where I have at least one good battery. So I'm going to take these ending spots of these trees. It looks like I have 3 different sequences here. And I'm going to add up all the different sequences that work. First sequence I had was good. Next sequence I had was a dead one and then a good one. And this final sequence was dead, dead, and good. Looking at these probabilities, probability of a good battery was 16 out of 20. Dead and good. Dead is 4 out of 20 to start. 16 out of 19 for the next poll. Dead, dead, good. Dead is 4 out of 20. 3 out of 19. 16 out of 18. I'm taking all of the sequences that work. If it's a long sequence, I'm multiplying those values together, and I'm adding up all unique combinations. When I did this, I ended up getting something like 0.996. 9965-ish. So there's roughly a 99.65% chance that I'm going to get at least one good battery in this poll. What if I wanted the opposite probability that none of the batteries here were good? Well, if none of the batteries were good, then that sequence that I care about there would be dead, dead, dead. None are good there. I'm going to multiply these together and see what I get. 4 out of 20 for the first, 3 out of 19 for the second, and 2 out of 18 for the last. 4 out of 20, 3 out of 19, 2 out of 18, and that gives me 0.0035 or so. Now, linguistically, the opposite of having at least one good battery would mean all of those batteries were bad, or none of them were good. So you might notice something about these two probabilities. If you were to take these two numbers and add them up, you end up getting 100%. So either you have at least one good battery, or you have no good batteries. There's actually a name for these kinds of pairings. They're called complements. The complement of an event is everything else in the sample space except for that particular event. It's denoted A with a C. A with a C is just a fancy way of saying it's not A. So if the probability that you win a game is, say, 25%, the probability that you don't win would be 75%. It's everything but that. They add up to 100%. They're opposites. One important example of this complement rule is the opposite of at least one is 1 minus the probability of none. So you're either going to win at least once or not at all. Those are the only two things that could happen. They're complements or opposites of each other. So instead of adding up all of these sequences that work, we might have some shortcuts to find these probabilities in the future. The best way to find these, practice them. So I'd like to try to do one more of these problems, just practicing it with you. And this is going to bring a lot of these elements together. So this might be one that you go back and practice a few times to get used to it. So this is some real data here. Studies have shown that 74% of people in the men's restroom at an airport wash their hands. 84% of women, individuals in a women's restroom wash their hand. Suppose that there are 40 individuals in an airport lounge that identify as male and 60 that identify as female. This is by the American Society for Microbiology. They're assuming a gender dichotomy here. I think it would be really interesting to see what this would look like in a non-binary setting. That might be some probabilities worth examining. What is the probability that the next person to use the restroom does not wash their hands? I'm looking in my head and I'm just sort of thinking about what could happen here. And this feels like a sequence of events because you have the next person here is either going to go into the men's or the women's restroom. 40 out of 100, 40 and 60 gives you 100. Identify as men. And 60 out of 100, or 60%, identify as female. For the male group, 74% wash their hands. So I'm going to use a little bit of an abbreviation here, W with the C to mean does not wash their hands. While 74% of people in the men's room are washing, that would mean the remaining 26% are not. For the women's group, wash or don't wash. 83% in the women's room wash their hands. So the remaining amount, 17, do not. I want to know the probability of not washing hands. So I'm looking at those spots in the tree. So I'm going to be looking at the sequences for men that don't wash, women that don't wash, and I'm going to add these together. Men is 40%, not washing is 26%. Women is 60%, not washing for this group is 17%. I'm going to type this into a calculator and I'll see what I get. And I get a probability of about 20.6% chance that the next person does not wash their hands. When I saw this, I saw it as a sequence of events. You enter the restroom, you wash your hands afterwards. That's why I decided to use a tree, because it was a sequence. You might be thinking, okay, But could I do a table if I really wanted to? Well, let's try that out. I have men and women, and I have wash and don't wash. On the outside, I'm putting totals. And if you had more groups that you wanted to include in your columns, it doesn't have to be 2 by 2. You could have as many columns as you want to this thing. In total, I'm looking at 100% of people. So I got that 100%, or as a decimal, 1.00 that I'm going to be putting in this right-hand corner. Looking at the problem again, I'm seeing that 40% were male. So the total here for men is 40%. The total for female was 60%. Right off the bat, one of my numbers doesn't make sense though. It says 74% of men wash their hands. So you might be thinking, I want to put 74% into this square, but it add up more than the total already allows me. And that's because it's not 74% of men and wash, it's 74% of men belong in that category right there. So this is not going to be 0.74, it's 0.74 of the 40. 74% of the men. So 29.6% in this total area would be men that wash their hands. Doing the subtraction here, this means that 10.4% of this entire area are men who do not wash their hands. For women, 83% of women wash their hands. So this is not 83% total for both out of everyone. It's 83% of the 60. When I'm multiplying those together, 83 and the 60, this gives me 0.498%. Looking at the totals, if I want this to add up correctly, this should be 102. 10.2% are women that don't wash their hands. Adding up horizontally, this gives me 0.794, or 79.4% wash their hands. And adding these together, I get a total of 20.6 that do not wash their hands. In total, the amount that don't wash is 20.6. In total, the amount that don't wash is 20.6. I get the same answer for a tree that I do for a table. So for a lot of these problems, you actually have the choice between these two pictures. Sometimes it's going to be easier to create these types of trees. Trees are easier for sequences. Sometimes it'll be easier to make a table. You'll discover that tables are easier when you're dealing with combinations of events. This lesson folder has a lot of additional example videos on using both trees and tables, and I would strongly recommend that you watch those. Even more than just watching problems though, try some out for yourself. You got a list of problems here that you can go through on your own to check out to make sure you understand what's going on. It takes some while to get used to this new concept. Great to do this video with you.